I'm pretty sure you have seen this many times by now, but I'm still going to introduce what is important for this talk, and I think that will be a nice revision for you. So, two types of neutron scattering. Number one is elastic neutron scattering. In elastic neutron scattering, there is no exchange of energy between neutron and your sample. And the only thing you are looking at is the change in momentum or direction of the neutron. The second one is elastic neutron scattering. In elastic neutron scattering, there is an exchange of energy between neutron and your sample, as well as you are looking at change in momentum or direction of the neutron. You can scatter vector K prime, which you can calculate by these triangles, which you have seen already. So scattering quantities, so the measurable quantity is a neutron differential scattering cross section. And by measuring this, we get what we call dynamic structure factor SQ omega in energy domain. Now, dynamic structure factor SQ omega is the one that gives us information about the dynamics. Now we can break this SQ omega into two: coherent dynamic structure factor and incoherent dynamic structure factor. Now this coherent dynamic structure factor here gives us an idea about pair correlation function. So this is what you typically measure in a neutron spinnaker experiment. The second part is incoherent dynamic structure. Incoherent dynamic structure gives us an idea about single particle correlation function or self-correlation function. So in my talk today, mainly I will be focusing on this because you have already had enough of coherent scattering, I guess. Okay, just to summarize again, we have two types of dynamic structure factors, S incoherent Q omega and S coherent Q omega. Now, you measure SQ omega by spectrometers that operate in energy domain. So today, I will mostly be focusing on SQ omega, not on SQT. However, if you perform Fourier transform, inverse Fourier transform with respect to omega, you go from omega to time space. And you have S incoherent QT and S coherent QT. So this is intermediate scattering function, and this is what you measure directly by neutron spinnaker. If you perform Fourier transform one more time, this time with respect to Q, you go from Q to R space, and you end up with what we call correlation functions. Now, these correlation functions you can calculate directly if you do simulations, which is one of the complementary methods for neutron spinnaker and neutron scattering in general. Now, these correlation functions are very easy to understand. There's a very simple definition for them. So, G self RT here is the probability of finding a particle at position R after time t if that same particle, remember this is important, we are talking about the same particle was at position 0 at time t equals 0. Hence the term self-correlation function. So basically in this case, you are tracking that single particle and you are trying to figure out where it is going as function of Q and T. The second is G pair, which is the probability of finding a particle at position R after time t if there was a particle at position 0 at time t equals 0. So this is the pair correlation function. So now you can see the dynamic structure factors or intermediate scattering functions, they may look very different, but they are directly related with correlation functions, which you can understand rather easily. Okay, so types of scattering, again, we are looking at the data in energy domain now, not in time domain anymore. So here is a sketch of SQ omega versus energy transfers. So again, we have two types of scattering, elastic neutron scattering. Now this elastic neutron scattering appears as a narrow P with zero energy transfer. This basically gives us an idea about instrument resolution, as well as it gives us an idea about slower processes that an instrument cannot resolve. Okay, so then the inelastic scattering, we can break it into two. One is quasi-elastic neutron scattering. This quasi-elastic neutron scattering, it appears as a broad peak on the top of the elastic line, and it peaks at zero energy transfer. Now this broadening here, you can see, it is much broader if you compare it with elastic line. So this broadening gives us an idea about diffusive or diffusive-like processes in your sample. The third one is elastic neutron scattering, which shows up at non-zero energy transfer, as you can see. And this type of scattering gives us an idea about vibrational or fast modes of your system. So just to remind you again, not to confuse, only two types of scattering. Elastic and inelastic scattering we can break into two. Quasi-elastic and the other one is inelastic scattering. Make sense? Okay. So now you have seen this. Now let's have a look at the scattering types in a broad picture. So what we are looking at here is dynamic structure factor again, but this time we are going to much higher energy transfer. So again, at omega equals 0, you have elastic scattering, on the top of which you have quasi-elastic neutron scattering, which gives us an idea about diffusive processes. Now, if you go to higher energy transfers, then you will see what we call phonons. And these phonons are basically nothing but collective vibrations of atoms in crystals and lattices. And this is coherent inelastic scattering. If you go further, if you go to even higher energy transfer, then you will see inelastic peaks. And these inelastic peaks are because of molecular vibration. So we can actually look at all of these here at the NCNR by using different spectrometers, which some of which you will see tomorrow in the afternoon when you take the tour. But in my talk today, I will mainly be focusing in this region. Okay. All right. So now you know how does the quasi-elastic broadening looks like. So what can we learn from it? So here is the Fick's law, and GSRT is the solution of this equation. So if your system is going through simple diffusion, then you know that the function form, you can solve this equation, and GSRT is going to be given by this equation, where D is the diffusion coefficient of that diffusing particle. Right? Now, if you do MD simulations, you can calculate this function from the trajectory of your atom. Right? Now, if you perform Fourier transform and you go from R to Q space, you end up with functional form for intermediate scattering function. So if you have simple diffusing species and you go to neutron spinnacle and you do an experiment, then this is the functional form you will be using to fit the data. And D is again the same diffusion coefficient. If you perform Fourier transform one more time and you go from E to omega space, which is what we are going to see today, then you end up with what we call Lorentzian function. Now, in this Lorentzian function, this gamma here is nothing but and the interesting thing is, this gamma, which is full width half max of the broadening, is directly proportional to D times Q squared. So what this means is that if you measure Q dependence of that broadening, it's directly going to give you diffusion coefficient of your diffusing species. Make sense? So you can see that this quasi-elastic broadening and its Q dependence is very important. Okay, so this was simple diffusion, but we don't have it all the time. So typically we deal with what we call jump diffusion model. So what happens in a jump diffusion model, that a given atom is going to wait for certain time, we call it residence time, and then it's going to make a jump to next location. Stay there for that residence time and then make another jump. So this is called discrete diffusion or jump diffusion. So how does that work? So here we are looking at full width half max as a function of Q for 3 different models that deal with jump diffusion process. So the first one here is Chudley-Elliott model. Now this model assumes that all of those jumps, they are of equal length, R. Now as you can imagine, that this type of model is not really going to work very well in soft matter, because in soft matter, you assume that there will be a distribution of jump lengths, right? Because of the amorphous nature of your sample. So this type of model works better for crystalline materials, where distances are fixed. Now these two models here, they deal with soft matter, jump diffusion. So the first one here is called Hall and Walk model, and this basically assumes that these jumps, they have a distribution, and that distribution is Gaussian. The next one is SS model, and this assumes that these distributions of jump lengths is exponential. So as you can see from the Q dependence of full width half max, they all have very distinctive Q dependence. So you can fit the data of broadening, and you can figure out what type of diffusion process you have in your system. Make sense? Okay, so one more quantity that you extract when you are doing the fitting is EISF. So full form is elastic incoherent structure factor. So for a simple diffusive process, EISF is going to be 0. All the signals will have quasi-elastic broadening and no. So how do we define EISF? EISF, as you can see, is the fraction of elastic signal over total signal. Okay? Now this EISF is going to be non-zero if you do not have a long-range diffusive process, but rather you have a process that is confined. So, for example, maybe you're looking at water dynamics and it is confined within a pore, for example, MCM41, or maybe those water molecules are confined in biomolecules, for example, between paper sheets, and they are performing motion which is confined. And this EISF is going to be non-zero, and by fitting the Q dependence of that, you can figure out exactly what is the geometry of that motion. Okay, so here just to give you an example, I'm showing you Q dependence of EISF for n equivalent sides which are located on a circle. So for n equals 2, it's like a dumbbell type of motion. For n equals 3, it's like a motion on a triangle, which is what you would expect, for example, from methyl rotation. For n equals 4, it's like on a square, and for n equals 6, so it's on a hexagon. So you can see they all have very different Q dependence. So you can fit the data and you can figure out exactly the geometry of that confined motion. Okay, I'm pretty sure you have seen this before. So the two main neutron scattering complementary techniques for neutron scattering that we are going to discuss in this talk are backscattering and time of flight. So backscattering covers like slower side of these time scales. So it goes, if you look at the slower side, maybe up to few nanoseconds, 5 nanoseconds or so. On the faster side, it goes to up to 50 picoseconds or so. Time of flight, on the other hand, covers faster time scales. So on the lower side, it goes, slower side, it goes probably to 100 picoseconds, and faster side, it goes up to 10 to the power minus 2 picoseconds. And the length scales covered by these techniques they overlap with neutrons, they go perfect for soft matter. Okay, I'm pretty sure you have seen this too as well, but so you know by now that hydrogen has very large incoherent scattering cross section in comparison to other typical elements that you would find in soft matter. So if you have hydrogen in your sample, then most of the scattering will be incoherent scattering from those hydrogens. And that means you are looking at single particle dynamics of those hydrogens. If you are not interested in single particle dynamics, but you want to study pair correlation function, then you will have to substitute that hydrogen with deuterium. And now you can see that most of the signal will be coherent scattering from oxygen, deuterium, and carbon. And now you are looking at pair correlation function. So in this, for example, little sketch here, we want to study single particle dynamics of component B. So this is the only one that is hydrogenated. This one is deuterated, so we don't see this. We get very little signal from it, so we can follow selectively component B. Okay, so that's how instrument resolutions and spectra look like in frequency domain. So you can say that these are instrument resolution functions for different spectrometers. So the U one here, which is very fine, will be for backscattering spectroscopy. spectrometer. And these other three broader one, they will be for time of flight. Okay? So instrument resolution, meaning full width half max of the elastic line, is going to define what is the slow dynamics that you can resolve. Okay? And you know that you are going to have there is going to be a range of energy transfers. That's what we call dynamic range. Okay? Faster side of that, or this one, is going to define what is the fast dynamics that you can analyze from that data. So again, elastic line, full width half max, we call it instrument resolution. It tells you slow process that you can resolve. And dynamic range, meaning the range of energy transfers, that tell you what is the fast process you can resolve. And in between. Okay, so a quick slide about backscattering spectroscopy. So backscattering spectroscopy, remember the fine blue curve in the previous slide. So we achieve final resolution by employing backscattering geometry, and what that means is, so here we are looking at wavelength spread for a Bragg diffracted neutron beam. So now we want to minimize this because remember that it was very fine line. So how do we do this? So what we can do is we can choose 2 theta to be 180 degrees, and then contribution from this term will go away. Hence the term backscattering because of 180 degrees. So there are 2 important components for this spectrometer, monochromator, which are made of silicon 111 crystals, and by using this we get a single neutron wavelength of 6.27 angstrom. Then we also have large arrays of analyzers. We use the same crystals there, silicon 111 crystals. So by doing this, we achieve instrument resolution of 0.8 micro eV. If you convert it in time, it will be about few nanoseconds. This is the slow side of the instrument that can resolve. Then dynamic range is plus minus 36 micro eV. So here in the United States, we have one more backscattering spectrometer. It's called BASIS. The instrument design is given here. It's a spallation source-based spectrometer, so it looks very different. And this instrument offers instrument resolution of about 3.4 micro eV. And the dynamic range offered by this spectrometer in standard mode is plus minus 100 micro eV. Okay? Okay, now just one slide on time of flight. So how exactly we do it? So in this case, we simply follow neutron time of flight. Okay? So you are following neutron time of flight, but to do this, you have to know at what time where they are. So that's why you have to introduce pulse nature to the neutron beam. Because when you make the pulse, you know all of these neutrons left at this time, right? So you have a bunch of choppers here. So some of them are pulsing choppers, you know, they are rotating at high speed, and neutrons can only pass through from here. So you introduce pulse nature. Then you have frame removal and order removal choppers. What they do, basically, they remove some of the contaminants from the neutron wavelengths. Then finally, you have monochromatic choppers. And after that, we have a very fine monochromatized neutron beam. So energy resolution for this is given by this equation here. As you can see, it's equal to W. So if you want to achieve higher energy resolution, you have to use longer wavelength neutrons, right? So this is the actual time of flight. So this is distance and this is time. So neutron leaves from here, then they go through a bunch of pulsing choppers and whatnot, and finally here you have monochromatic choppers. So after this point, we have a highly monochromatized neutron beam, right? Then it goes and hits the sample here. Now, if there is no exchange of energies between neutron and your sample, then this neutron will scatter elastically and it will be detected by detectors here, right? Now, if this neutron or some other neutron actually gains some energy from your sample, then this neutron will reach detectors here rather quickly. However, if the same neutron or other neutron, it loses energy, then it will take much longer to reach detectors, right? Now, because we know these distances very well, by following the neutron time of flight from here to here, we can figure out exactly how much energy a particular neutron has exchanged with your sample. That's time of flight. Okay? All right, so this is all about techniques. Now we are going to see some science examples. I guess the interesting part, right? Okay, so my first example shows the relationship of relaxations and toughness in polymer glasses. So the base material for this work is polycarbonate. A polycarbonate offers excellent impact strength. So what I mean by impact strength is that if you have a bulletproof window, whether a bullet is going to really cross that or not, it depends on the impact strength of that material. So polycarbonate offers excellent impact strength and it is used in bulletproof windows. So what we are doing in this work, we are mixing polycarbonate with aerochlor, or in the second system, we are incorporating 1,4-cyclohexane linkages directly into the polymer backbone. And by doing this, what we are doing is we are systematically changing that impact strength of polycarbonate. And we are looking at the dynamics at the same time. And see if there is a correlation of if we can learn something. So here we are looking at mean square displacement. Now this mean square displacement, we can calculate from the elastic line. Remember the new, elastic line of the spectrometer? So we can follow that elastic line, we can, as a function of temperature, and we can calculate what is one mean square displacement. Now this mean square displacement, as you can imagine, it gives us an idea about mobility or dynamics of the system. Higher the mean square displacement, faster the dynamics. Make sense? So here we're looking at that mean square displacement as a function of temperature. You clearly see that in the low temperature regime, mean square displacement increases linearly with temperature. Now this is due to vibrational contributions, not the interesting part. Then at around 200 Kelvin, there is an upturn in mean square displacement. This is due to a new dynamics, right? So we can calculate contributions from this new dynamics, which we call excess mean square displacement at 300 Kelvin here, because we are measuring impact strength measurements at 300 Kelvin, okay? So this is the interesting temperature. Now, if you look at this, you can clearly see that as you add more and more aerochlor, mean square displacement actually goes down. So that means dynamics is decreased, it's slowing down, right? Now, if you look at isode impact, which is the impact strength, as a function of aerochlor, as you can see very clearly, as you add more and more aerochlor, impact strength goes down. That means you are making polycarbonate brittle. It's less tougher now. Now, if you look at the second system, again, we have similar behavior, linear regime at low temperatures because of the vibrational contributions. Then there is a new dynamics at 200 Kelvin, and we can calculate excess mean square displacement due to that new dynamic. However, you see a very different behavior if you compare this with this one. You can see when you add 1,4-cyclohexane linkages, mean square displacement is always higher if you compare it with neat polycarbonate. So that means dynamics is increased when you add 1,4-cyclohexane linkages. Now, if you look at isode impact, which is the impact strength, as you add more and more cyclohexane, impact strength also goes up. So now we can look if there is a correlation between the two. So here we are looking at impact strength as a function of excess mean square displacement. You can create, and this data is normalized to PC, so PC sits here at 1. Aerochlor makes polycarbonate less tougher, so those points are down here. 1,4-cyclohexyl linkages, they make polycarbonate tougher, so they are up here. And as you can see that there is a clear correlation between the dynamics and impact strength. Higher the mean square displacement, tougher the material is. So we wanted to learn a little bit more about what is this new dynamics. So we made full quasi-elastic measurements on time of flight spectrometer here at DNC and R. And here is the data. So you can clearly see this is the data at low temperature side. So you can clearly see, you see a peak close to elastic line. Now this peak is what we call boson peak. This boson peak gives us an idea about collective vibrations in these soft materials. Now if you go to higher temperatures, you can clearly see that boson peak is still there, but now you have a standard quasi-elastic broadening because of relaxations. So we have two processes, boson peak and quasi-elastic relaxations. So we can model them appropriately with different models. And here we are looking at peak amplitude. Peak amplitude means how strong a process is as a function of temperature. So you can clearly see that boson peak retains the same intensity over the entire temperature range, right? But quasi-elastic relaxations, they grow as a function of temperature. And what is important here is that the temperature at which quasi-elastic relaxations take over boson peak is not far away from where the material goes from brittle, meaning less tougher, to ductile mode, meaning where it is really tough. Okay? So what happens here in polycarbonate is that at low temperature side, these quasi-elastic relaxations are either absent or very weak. And therefore, these materials are not able to dissipate impact energy via these quasi-elastic relaxations. However, at higher temperatures, these quasi-elastic relaxations are strong enough, and now these materials are able to dissipate that impact energy via these quasi-elastic relaxations. So these quasi-elastic relaxations are really important for that impact strength that you need. Okay? Okay, so my second example shows the correlation between the diffusion of water and performance in RO membrane. So as you know, water crisis is a real one. Right now, almost 2 billion people do not have access to fresh water. So how can we do this? So one way of solving this problem is through RO membranes, of course. So these RO membranes, they separate contaminants from the fresh water. So on one side you have contaminants and the other side you have fresh water, right? But we have to somehow improve their performance. So this is what we are trying to do here. So this is the model for that RO membrane. So you have polyamide active layer. The main ingredient is this MPD here with amine sites. Then you have polysulfone support, which is a porous support. And then you have some polyester fabric. Now, if you look at the detail of this material here, you can see it's cross-linked via this TMC. So why do we have to cross-link? So we have to cross-link this because by cross-linking, you can improve certain properties of this material which are needed for this purpose. So this does the cross-linking. Now we can control that cross-linking by substituting this TMC with IPC. Okay? So this is what we are doing here. So what happens is that when there is no when there is no IPC, cross-link density is highest, right? When cross-link density is highest, this material swells very little. So what I mean by swells very little, it absorbs very small amount of water. Okay? So when you remove this TMC and substitute it with IPC, you have lower cross-link density, and this material swells more. So now it basically absorbs more water. Okay? So membrane number 6 here is the one with highest amount of TMC, swells very little. Membrane number 10 is the one where we have maximum amount of IPC, so meaning it swells more, absorbs more water. Now, if you look at this here, this is the sodium chloride rejection. You can clearly see that when you swell membrane, actually sodium chloride rejection goes down. So it's absorbing more water, but it's not rejecting as much sodium chloride as it was before, which is okay. But this is also very surprising. This is water permeance, meaning how much water is diffusing through those RO membranes. That also goes down, which is surprising because sodium chloride is much bigger molecule if you compare it with water. So it's allowing sodium chloride to pass through, but it's blocking water. So what's going on here? So we measured mean square displacement. So again, mean square displacement against temperature. This is membrane number 6. Again, with higher cross-link density, swells little. So you can see this is a dry film, there is no upturn, so there is no dynamics, nothing. But when you hydrate it with H2O, you can see an upturn. Now this is due to water dynamics, okay? Now if you look at membrane number 10, dry looks similar, but then this upturn is much stronger. The reason is membrane number 10 absorbs more water, right? So it's more water, overall mobility is higher, mean square displacement is higher, makes sense. However, we still don't know why lower, right? We still don't understand that. So we made full quasi-elastic measurements using time-of-flight spectrometer. And here we are looking at the dynamics of water. So what we did in this case, we hydrate them with H2O, we hydrate them with D2O, and we subtract the D2O part. So that means contributions from RO membrane, they are subtracted. So here we are looking at water dynamics only. So here's the full width half max as a function of Q squared. So you can clearly see that at higher Q side, you get standard jump diffusion type of behavior that I talked about earlier. What is interesting here is that membrane number 6 shows higher full width half max in comparison to number 10. So that means membrane number 6, in membrane number 6, water is diffusing faster than membrane number 10. Which is kind of surprising because membrane number 10 is the one that swells more, so it absorbs more water, but water is not diffusing as fast as if you compare it with membrane number 6. So again, we looked at the EISF. You can see EISF is non-zero, so that means water dynamics is confined. Okay, so we can fit this data, and for this purpose we chose a Volino model. This model assumes that water is diffusing within a sphere. So if you are, depending on your Q value, if you are inside, then water will be diffusing normally. So you have jump diffusion type of model predictions, right? But once you go outside this sphere, they're not diffusing anymore, right? So you should see the same behavior in full width half max, and that's exactly what we see here. So you see at higher Q side, you are inside the sphere, water is diffusing normally, but once you go outside the sphere from the dimensions of this sphere, you see a flat behavior, which means that water dynamics is really confined. So this model works, everything is good. Okay, so from this you can say that this is the reason why we have lower permeability for membrane number 6. So here we are looking at a broad picture of water transport and associated mechanism. So here we have data from a previously RO membrane that we used. So this here is the bulk water data, and here is the water dynamics in MCM41. So this we call pore flow mechanism because water, if it's falling under this, is following basically the pore flow mechanism. So water basically diffuses through like it's diffusing through a pore. It's not interacting with whatever that pore is made of. However, if it's down here, then you have solution diffusion. So in this case, water is basically interacting with whatever that material is, in this case, RO membrane, and that may actually slow it down, right? So we looked at this a little bit more and we figured out why this happens. So what happens is that in number 10, you have a lot of unreacted amine sites. And these amine sites react with water and form hydrogen bonding when it's diffusing through, and that's why it's slow. So by doing this, we now have some insights and we can improve this formulation. Okay, so I think I should have shown this at the very beginning, but here we go. So now we are looking at simulations and neutron scattering. They go together really well, okay? So here we are looking at smaller Q values, meaning at large length scales. So when you are at large length scales, your polymers, they are going to look like bead and spring, right? This is what we learned in neutron spinning, right? So if you look at the structure, you have Gaussian chains, and if you look at the dynamics, then you are mainly looking at chain diffusion. So you will have reptation. Reptation is like a chain diffusing through, which is inside a virtual tube, which is formed by surrounding chains. And then you also have Rouse dynamics, which you have studied in your neutron spinning experiment, right? Now, when we go to larger Q values, meaning at shorter length scales, now you are able to see all those atomistic details. Okay, so you see how all local modes and everything. So this is what happens in fully atomistic MD simulations. So in MD simulations, you form a cell, put your bunch of your chains inside, you apply some realistic conditions like temperature, density, and so on, choose a force field, and you allow it to run. When you do this, the structure looks like this. So for polymers, you have usually two peaks. One is due to interchain distances, and the other one is due to intra-chain distances. Okay. Now, if you look at the dynamics, then you have alpha relaxations, vibrations, side groups, beta relaxations, and so on. You see all local modes, right? So all of this can be done by neutron scattering, and all of this can be done by simulations as well. So that's why they go together really well. Okay, so here I'm going to show you an example, recent example of polyisobutylene. So polyisobutylene is a little unusual polymer, and it has basically two methyl groups which are attached directly to the main chain. And then you have two hydrogens here. So what they wanted to study in this work, they wanted to look at the methyl rotations. Okay. So now, as you know, from MD simulation, you can calculate SQT. So we have SQTs for all possible atoms because you know positions of all atoms. So you can calculate SQT for not only for hydrogen or deuterium, for anything. So there they are. So and here we are looking at the correlation function for methyl hydrogens. This is 470 Kelvin, much higher than the glass transition temperature. So if you look at this data, you can clearly see that as you go to longer times, these peaks, they become broader and they move towards longer distances. So this is a classic signature of diffusion. So all good here. However, if you look at 320 Kelvin, which is now closer to TG, you can clearly see some signs of like two peaks here. That means you have alpha relaxation as well as maybe methyl rotations. So they wanted to learn a little bit more about, they wanted to get the rotational time scale. So how to separate it from alpha or the main chain, because you have the main chain is moving and then you have alpha methyl rotations. So they are methyl rotation, methyl basically is taking part in two motions, main chain as well as its own rotation. So when you have a situation like this, you can assume that they are statistically independent. If that is the case, then methyl rotation intermediate scattering function will simply be product of rotational part times alpha relaxation, right? Now alpha relaxation is nothing but the chain, so you can substitute methyl overall methyl FQT by chain hydrogens and see actually if it makes sense. Now when you do this, now you are looking at rotational part only. Rotational part, it's confined motion, so at long times you should see it should be compatible with EISF. That means there should be a plateau. So you see some plateau at higher Q values, but nothing on lower Q side. So by doing this and looking at EISF, they were able to conclude that in this particular case, that statistical independence does not work. Methyl rotations are strongly coupled with chain dynamics. Okay. I will skip this one, and this is just my last example. So in this example, I'm showing you some data from broadband dielectric spectroscopy. So what happens in broadband dielectric spectroscopy, you follow motions of dipoles. Okay, and what you measure is the dielectric constant. You have real part and imaginary part. Now, if that dipole is part of structural relaxation, then you can actually combine the data with neutron scattering and probably increase your temperature or frequency range. So this is what they did in this work. So here we are looking at the dynamics of biomolecules, tRNA and lysozyme. So as you know, when you have biomolecules and you hydrate them with water, only then they are functionally active. If they are dry, they are not active. So in early 2000, concept of slaving was proposed. In this, it was suggested that when you hydrate biomolecules dynamics and its activity is basically slave to the dynamics of hydration water. Okay, so this is what they wanted to check here. So these open symbols, they are from neutron scattering, all right? And this is the dynamics of biomolecules because they are hydrated with D2O, okay? So now hydration here is equivalent. So if the dynamics is really slaved, then there should have been exactly the same temperature dependence. Now, just based on neutron scattering data, maybe you can say that they are not the same, but you can't claim. So they combine data with broadband dielectric spectroscopy, and now you can see in the extended temperature range or time range, you can clearly see that this is different. And concept of slaving is simply not true. Okay? So that's how you can combine data from different techniques and gain more information from the neutron scattering data. And with that, I will say thank you, and if you have a question.
Question about your dynamic range slide at the very beginning, the one with the different peaks. Yes. Yep. So for the dynamic range, is that the beginning and end of the blue line, or is that the full width of maximum?
Yeah, it's this one here. So for example, you want to plus 20, so plus 20. And this one, it is just going to go like this.
I wasn't sure if it's the black half width at half maximum, or if it's the blue. Okay.
Yeah.
Any other question?
Yeah.
So, why do you use the fitting like that? The boring. How does it come? Yeah.
So here basically we have two processes. So if you look at the low temperature side is only the shoulder and no quasi-elastic dotting. But when you go to the higher temperature side, you see there is some contribution coming from boson peak, but now you also have on the top of that, you have a standard quasi-elastic dotting. So you have basically two processes. And that's why one of them is almost zero at low temperature side. But then if you go to the high temperature side, they both are present.
Can I ask a question?
Yes, sure. Go ahead.
You showed the simulation on the Matthew rotation. Why? How can SQT turn up?
I don't know, maybe.
I draw back the question.
I think
End of simulation, it's a
several,
simulation effect of the end of your.
several, yeah, it's already several nanoseconds, so I mean they cannot really claim that it really goes up. It's just Plato is there, so that's what they were looking for. But I think it's just you are really hitting the limit of simulations at this point.
But did the authors just get this result and they were able to see that they all
Resolution.
Which one?
like for anyone?
For in general. So usually what you do is, if you measure, for example, on backscattering, and then you realize that you need to go, you have signs of a slower process, then you will go to neutron scattering, right? And if you think that there is something fast, then you need to go to time of flight. Now, in time of flight, you can tune instrument resolution by choosing different wavelengths. So you have freedom. Now, how do you choose a particular one? Most of the time, we will have an idea like, okay, if it's this much fast, then maybe this wavelength will work. So you go there, measure the data for 5-6 hours, fit it, and if you realize that you are still not seeing it, then you change neutron wavelength and tune the instrument resolution pattern.
So there has to be fine tuning.
Yeah, so run experiment for 2 hours, choose your best temperature, and see if you can see that nicely. If not, then you adjust your wavelength.
Okay, let join me to thanks.